So it's pretty likely that you'll be asked to solve a differential equation at some point. It is slightly less likely that you'd be asked to solve one in context, but we have to look at that just to make sure that if it did come up, we would be able to deal with it. So differential equation in context normally are presented in terms of your displacement, velocity and acceleration. So this is something that you would have seen back when you were doing differentiation. So a good way of remembering this is dVA. So the way that I remember about that, most of you'll be learning how to drive a car just now, and you'll get your licence through the DVLA. The difference is that we don't have the L, so that's how you remember your order. So it's DV, we don't have the L, but you've got your A. Similar to with your Snapchat that you would have learned about differentiation, and you'll see in a lesson or two's time when we move on to integrating trig functions. If you differentiate, you go down the way. So differentiation means you're decreasing, you're going down the way. Integration would mean that you're increasing and you're going up the way. So if you have, D, remember, stands for displacement. If you have your displacement and you differentiate it, you would get velocity. If you have velocity and you differentiate it, you get your acceleration. Same applies in reverse, so acceleration would integrate to velocity and velocity would integrate to displacement. So that's just a good way of remembering the order that they go in. So this type of example, I've never really seen this show up in a past paper. The past papers tend to have a lot more numerical values in them rather than letters, but this will hopefully give you some understanding of how you would deal with a differential equation in context. So for this one, straight away it's standing out that it's talking about your constant acceleration. Over here, we're told that acceleration is a meters per second squared. We're told that time is equal to 0. And we're told that the velocity is u meters per second. For a question like this, I would always recommend highlighting or underlining, as I have done, just some of the key information. So it wants us to use the differential equation to show that the velocity at time t is v equals u plus at. So show that questions are always good because you know your answer before obviously you can get to it. So it sometimes makes it a little bit easier, sometimes not always. So it wants us to use that equation to find our velocity. So that is telling us that our acceleration, so if we think about this dVA, so remember down the way we differentiate, up the way we're integrating. So it is telling us that dV by dt landed us at our acceleration. So we've differentiated velocity and we've ended up at acceleration. So we now want to go back up to velocity. So what we want to do is differentiate A with respect to t. Now I didn't mention earlier on in the last slide, time is always a factor in these. So that t is always going to appear in your dv by dt. T is always going to be there because you differentiate or integrate with respect to t. So t is always going to be there. So if I am differentiating A with respect to t, that means I need to look for my t to appear. So for something like this, which is quite unfamiliar, I would always recommend thinking of it as something that is a little bit more familiar. So say, for example, if you have something like 3x plus 4 and you were asked to integrate 3x plus 4. When you integrate that, you would increase your power. So that would become 3x squared over 2 plus 4x. So when you've integrated that 4, you've made that x appear. And that is because we were differentiating with respect to x. So if you had something like 3 dp and you were going to integrate that, when you integrated it, you're integrating with respect to p, so you would end up with 3p, and then obviously that would have your plus c at the end of both of them. So for this one, when I've got a and I'm integrating with respect to t, it is going to become at plus c. And remember, that was us trying to find our velocity. So our velocity is the integral of our acceleration. So v is equal to at plus c. The question is telling us that it wants to know at time t. It wants us to show that it's equal to that equation. So remember, t is equal to 0. So if we take our velocity at a time of 0, we have got a times t, so we've got a times 0 plus c. The section up here tells you that your velocity when time is equal to 0 is actually equal to u. So we've got u is equal to a times 0 is just 0. So u is equal to c. So when we were doing our differential equations, remember the whole reason behind that was so that we could find this value of c. So we've now got this value here. So instead of having v equals at plus c, what we've actually got is v equals at plus u, which was just calculated. And if you compare this to what we were asked to find, they are the same thing. So that's us finished that section of the question. Moving on to the next one. So it starts talking about the distance travelled. So we've got t seconds. The distance travelled in t seconds is s metres. And it wants us to use the differential equation to show that the distance travelled from its initial position is given by that formula there. So we are looking to go from velocity back to displacement or back to distance. So to find that, remember your distance or your displacement is the integral of your velocity integrated with respect to t. Now, in that first part of the question, we actually figured out a formula for velocity, and velocity was at plus u, and that is what we're going to be integrating with respect to t. So if I integrate that, I end up with, so a, increase my power, I get at squared over 2 because I need to divide by my power, plus ut, and then plus c. So remember, this question is telling us that the distance travelled in t seconds is s metres, so I can now replace my distance by s. So this is our formula so far. We now need to start subbing our values in because it's a differential equation. We need to deal with this plus c. So again, we know that in its initial position, its time must be equal to 0. So similar to the last question, we are looking what happens when our distance is equal to 0. So replacing all my t's by 0, I've got a half a 0 squared plus u times by 0 plus c. My distance when it's in original position, so its time is equal to 0, but its distance is also equal to 0. So s of 0 must be equal to 0. Over here, this half a 0 squared is just going to give me 0, plus u times 0 is just going to give me 0, plus c. So for this one, c must be equal to 0. Again, we have to substitute that back into our equation. So replacing our c by 0, we have got that s equals a half at squared plus ut. And again, comparing that to what they wanted us to find, that is what they were looking for. So that must be your final answer down there.